Okay, for the next lesson, we are going to be looking at how do we make our graphs more accurate with respect to how a graph is going up or increasing or how it is going down or decreasing. So the first thing we're going to look at is concavity. Okay, so if we have a graph right here and it's connecting going from A to B, and let's say we know that this graph from the first derivative, we know this graph is increasing on the interval from A to B. How should we connect A and B to draw an increasing function? Should we draw a straight line? Should we have it kind of curving upwards? Should we have it curving downwards? How do we know what sort of increasing function it is? So I'm going to give you a couple of different options. So let's say this is F and this is G. So F is one option, G is one option. They kind of make like an I looking thing depending on which direction you do it. So we are going to define F is called concave downward, and G is called concave upward. And so F is curving so the curve opens downward, and G is curving so that the curve opens upwards. So how can we define this a little more formally than kind of curving downwards or curving upwards? Well, if I draw the tangent lines in for F, one thing I notice is that F is always below the tangent lines and G is always above the tangent line. So we're going to use this to define concave upward and concave downward. So definition, okay, if the graph of F on an interval I lies A below all of its tangent lines, it is concave downward. And I may just call this concave down sometimes. It means the same thing. And if it is above all of its tangent lines, it is concave upward. Okay. And we also give a name. So this is on an interval. So most functions have parts of them that are both concave downward and concave upward. So if I have some kind of function, it may have different periods of being concave down and concave up. So there is a point here where I have a concave, we have a concave down, and we have a concave up piece, and we also have a point in the middle. And this point here is where we switch from concave down to concave up, or vice versa, from concave up to concave down. And we call this a point of inflection. Okay. And a point of inflection is where concavity changes. So where you change from being concave up to concave down or concave down to concave up. Okay? So let's look at example 1. Okay, and we'll talk a little bit. So it's where concavity changes or something else is happening with concavity. Okay, so let's look at, okay, right where F is concave upward and concave downwards. And I am just going to write down and up. Let's draw a really beautiful, intricate graph. So we've got our x-axis and our y-axis, of course. So we are going to go up, down, up. Let's kind of curve back up that way. Maybe just go down that way. Then go over here, and then down again. So 1. It's not really a vertical tangent. Yeah. Got a little point there. switching from being more like there. Then as we go over, we kind of have a region that's flat, and then we go back up, and here, and here, and here. Okay, so let's keep that more like that. Okay, so now we've kind of identified all the points where we're changing concavity. So this here is concave down, this is concave up. This continues to be concave up. We haven't really switched. If we got a straight line, we haven't really switched to being concave. If you have a straight line, that's neither concave up nor concave down. So straight lines are just themselves. So we're kind of going to stop here, and that's a straight line. So this right here is still concave up. Flat lines are neither concave up nor concave down. Here we are down. Here we're up again for a second, and then we're back down. So concave, it's important to just recognize in a graph what those different concavities look like. So without drawing a graph, is there a way that we can tell the concavity? Because what would be the most useful for us is to be able to identify concavity from an equation so that when we're graphing, we can tell what regions we're going to be drawing as concave up and what regions we're going to be drawing as concave down so that we can graph curves that we haven't actually seen before. So what we're going to do is we are going to introduce our test for concavity. Okay, so if f is twice differentiable, which just means that the first and the second derivative both exists on an interval I, then, okay, if f double prime of x, so we're looking at the second derivative of f of x, is greater than 0 for all x on the interval, then f of x is concave up on I. And number 2, if f double prime of x is negative for all x on the interval, then f of x is concave down on I. So when so here we're not looking at the derivative, we're looking at the second derivative. So when the second derivative is positive, we are concave up, which means the derivative is increasing. And if the second derivative is negative, we are concave down, which means the derivative is decreasing. Okay, and so the second derivative isn't just useful for determining concavity. We can use this in order to help us find local extrema. And many people find this second derivative test to be actually easier than the first derivative test if you're just asked to find and determine the nature of the local extrema. If you don't have to draw a graph, you don't have to do anything additional. The sketching first derivative test is useful when you're trying to get to a curve sketch. The second derivative test is useful if you've just been asked a simple question, find any maximums or minimums, and you're just trying to do that. Okay, so the second derivative test, and this is more useful for things like polynomials where taking the second derivative is usually fairly easy. If it's something like a rational function, you may want to use the first derivative test. Okay, so for finding local extrema, okay, let f double prime of x be continuous on AB such that, and you'll see that abbreviation for such that probably from math professors, such that C is in AB. So you have some C in an element of this open interval. Okay. And f prime of x equals 0 at C. Okay, so you have a first derivative that's 0, which means we have a critical point at C. Okay, and it has to be equal 0. It can't be one where it doesn't exist. So then, because if it doesn't exist, then f double prime likely also won't exist. Okay, then A F has a local maximum at C if F double prime of C is less than 0. So if F double prime of C is less than 0, remember, we are concave down. So think about that picture. So C is, F double prime is negative, we're concave down, C is a maximum. And B, F has a local minimum at C if F double prime is positive. So when F double prime is positive, think of this picture. We have concave up and we have our C here. So this is concave down for a maximum and concave up for a minimum. Sometimes it gets a little confusing because it's a negative second derivative. That gives you a maximum and a positive second derivative that gives you a minimum. So I really advise you to think about what it means in terms of the concavity, because that's what's going to help you really determine whether you have a local maximum or a local minimum.